discuss about the classification of the FPGA structures. So based upon the placement, of the logical elements or the programmable interconnection and the memory. So there are different types of classifications what we can do it for the FPGA structures. So the first one we call it as a symmetrical array structure, the second one we call it as a row-based architecture, and the third one we call it as a hierarchical PLDs. So the first one is FPGA symmetrical array. So in this symmetrical array, as the name indicated, the logical elements we are going to place in a horizontal and a vertical manner. On top and bottom of these, we are going to sandwich these logic blocks through the use of the interconnect laid between them. And along with this, at the outer part of your symmetrical array, there is an IO block and a input-output block at the left side also and at the right side also. And each your logic blocks, it will be consisting of an n input lookup table. So this n input lookup table will give you us the relationship between the input and output sections. So what at each the CLB it is working on that, and we will be providing the routing path depending upon the interconnection of the elements which is needed for us to do the logical element connection. So this, as based upon the name indicates, it is called as a symmetrical arrays because we have placing the logical blocks in a symmetrical manner, and the input and output blocks also it is possible for us to create or implement in a symmetrical manner. So because of that, it is called as a symmetrical array. The next one we call it as a row-based architecture. In the row-based architecture, the logical blocks are placed in the form of rows, and the routing channels we are going to sandwich between the logical elements. And over both the sides of these logical blocks, we are going to place an input blocks and IO blocks. It not only on the left sides and right side, and also we are going to place the IO blocks on the top and bottom. So since we are placing these logical blocks in a row manner, so therefore it is called as a row-based architecture. And this row-based architecture, where the logical blocks are interconnected through the use of interconnected tracks, or we call it as a routing channels. So it's not only have one routing channel between the two logical blocks, so we have a multiple interconnect tracks between the logical blocks. So the IO block is located in the peripheral of each rows, and one row may be connected to the adjacent row via vertical interconnects. So one row we can able to make interconnect with another row through via vertical interconnect also it is available. And these logical blocks, it's not only responsible for us to do the implementation of the sequential elements, but we can also do the implementation of the combinational circuits also. So we can do the implementation of combinational elements and also the sequential element with the use of the Boolean expressions and also with the use of the flip-flops. Okay, so this sequential model can be used for the implementation of the complex combination and the sequential functions. Okay, so the FPGA, the row-based architecture, it is we can able to implement or we can able to create the FPGA through the use of this row-based architecture for a complex combination or a sequential elements. The next one we call it as a hierarchical PLDs. So in this hierarchical PLDs, so the design aspects or the logical blocks we are going to replace or we are going to place based upon the top level representation or the top level realization. So you can see here the IO blocks are placed at the outer part of the structure, whereas the logic modules, they are not in a symmetric row and a column manner. The logic blocks are placed upon the hierarchical manner, so depending upon how they are interfaced for each IO block. Okay, and each IO block, it is consisting of a large number of IO modules, and these IO modules, it may be in combination circuits also, or it may be in sequential circuits, and we can able to establish a communication between one logic blocks to another logic blocks, and also we can able to establish a communication between one logic blocks to the one more IO block or within the logic blocks through the use of programmable interconnect arrays. So these programmable interconnect arrays, we are going to interface from one logic blocks to another logic blocks in the form of hierarchical manner. So therefore, this architecture we call it as a hierarchical CPLDs. So if your design is based upon the top to down approach and it is having a several layer architecture, means then we can able to design such a system through the use of FPGA hierarchical PLDs, that is a programmable logic arrays. With the use of that, we can able to create a hierarchical implementation. Okay, so this is also called as a one of the structure form of representation of your FPGA. So next, let us talk about what is the difference between then FPGA and a CPU. With the use of this CPU, can we replace the FPGA, or with the use of FPGA, can we replace a CPU will be given in this slide. So you can see here, the CPU, it is nothing but it works upon some instructions and a memory. So whatever the program you are going to write, so that program you are going to represent in terms of instructions, and instructions will be executed. That is, it may be with the use of ALU, we can execute the instruction, and output of that we are going to store it in a memory. So means what, there is a one-to-one mapping is between memory to CPU or representation, or that is a microprocessor. But that is not in the case of your FPGA. So you can see here the FPGA, we have the logic blocks, we have a memory blocks, and the interconnection of one memory blocks to another logic blocks, and also with the logic blocks is possible. So means what, it is not a single layering architecture in the FPGA, it is there. Where in the case of microprocessor, there are two entities you have. One is a memory entities. In that memory entities, we have divided into one is the instruction set, and one more we call it as a memory set. And this instruction and memory set directly it is connected to CPU. That is a peer-to-peer entity connection. It is there, but that is not present in your FPGA programmable gates. So the programmable array, that is a programmable implementation, we have represented into logic blocks, and these logic blocks are interconnected from one logic block to another blocks with the use of programmable interconnectivities, and also we can able to implement the logical elements and also the sequential elements from this FPGA. So this is the fundamental difference between your CPU and FPGA. Okay, the next one. So what are the key techniques, or what are the key performance parameters we need to see in the case of FPGA based design system? Means these are the following key important techniques what you are going to measure in order to see the performance of a FPGA based subsystem design. The first one is a performance. Okay, so how best you are getting the desired result, so that represents your performance. Okay, so and how quickly you are going to get. So it may be in terms of measuring the throughput, or it may be in terms of measuring the latency. So that when you are measuring the throughput and latency, the clock rate what we are going to use to measure the performance, that also plays an important role in the case of FPGA based design subsystem. The next one we call it as a power and energy. So since in the FPGA system we are mainly talking about a programmable interconnects, that is a routing path we are taking care of that. So the routing path, how you are going to do the establish or how you are going to do the interconnection of this IO block with your logical blocks, and how you are going to interface these IO block and logical blocks with the sequential circuits. So based upon that, your power factor will be calculated. Okay, so the energy, or the we call it as a power budget, so with which power budget we can able to energize each component of your FPGA. So based upon that also the performance of your the circuit or the application will rely on. So the power budget or the power which has used in order to the excitation of the subsystem, it has to be minimum. And if any subsystem or if any logical block, if it is not functioning, means then it should consume a minimum amount of power in the idle mode. Of course, we know that all the subsystem or the logical element, even they are in off state, so they will consume some amount of power, but the amount of power they are going to consume, it has to be as minimum as possible. The next one is the design time. Yes, we know that the FPGA will produce a better performance when you compare to your complex PLDs and PLDs. But what is the design time it is taken, or what is the amount of time the manufacturers will spend in order to do the completion of your task? So that also plays an important role in the design of any subsystem. So since there are different entities are there for us to do the programming, so there are available lot of tools are there nowadays. So it is very easy for us to do the implementation or the design aspects on top of the FPGA subsystem. Okay, so if your prototype and if your constraints of your design are well clear and they are well established, means then the design time in order to implementation of your prototype will be done in a minimum time only. But the thing is, so you need to define your problem or the application properly, and how your application has been divided into subsystem you need to define, and how these subsystems are interconnected from one subsystem to another subsystem, and what are the device constraints and also the constraints which are given by the customer. So all those details has to be clearly defined. So if all these things are defined clearly, means then we can use a minimum time for the design process for the implementation of your FPGA based design subsystem. And the next one is the design cost also plays an important role in the measuring the performance of the FPGA based design subsystem. Okay, it's not that you're going to create a miniature component, but also what is the amount of that is money we are going to spend on the implementation of the design subsystem also plays an important role. So generally these FPGA, as we said, they are programmable logic devices. So if you run any application on this FPGA, and if you don't want to run this application in the next subsequent years or the next subsequent timings, then we can able to reconfigure that application, and we can implement or we can able to install one more set of applications program. So therefore the design cost of reconfiguration is very less in the case of FPGA based design methodology. Since the design cost and the design for the manufacturing time is very less, so therefore the manufacturing cost also it is very minimum. So why? Because of the advancement in the VLSI technology, that is with which the large number of ICs we can able to incorporate in the miniature component. So because of all these advantages, so we can create this FPGA with a very minimum cost. Of course, we know that this FPGA generally they are more expensive when you compare to your ASIC design because of the programming manner. But if you want to measure the overall performance of the system, or if you want to implement the very complex subsystem, in the case of your ASIC design or also in the case of PCBA design, this FPGA based design will yield us a minimum manufacturing cost when you compare to the remaining technologies. Then, so these are the performance measurements what we are going to use in the FPGA design manufacturing process. Then the next one is, so what are the challenges we need to go? What are the challenges we need to face, or what are the challenges we are going to face during the implementation of your subsystem through the FPGA? That also has to be studied. So the first one we call it as a multiple level of abstraction. Multiple level of abstraction. So as I said you, so when you want to design any applications, the idea or the solution what you're going to come up for that problem, it has to be clearly defined along with all the constraints what we are going to undergo during the manufacturing process. So if your specifications and if your constraints are properly designed means, then the creation or the selection of the architecture will be very easy. If your abstract level or if your abstraction of the problem along with the specification, if it is not clearly defined means, then it is very difficult for us to select the design methodology or the design process or the design flow what we are going to select for the particular problem implementation. It will lead to a problem. So that has to be studied properly. So the next one is multiple and conflicting cost. Okay, so since this FPGA are very expensive, that is the hardware components are very expensive, so it is necessary for us to know so what is the amount of the implementation cost we need to measure. Okay, so at the initial stages only, so the implementation cost, the hardware components, the amount of hardware component which is required for us to do the implementation, it has to be analyzed properly. Along with this, we need to see what is the power consumption of each final FPGA. We also take care, because the power factor is also plays an important role in the calculation of the cost entities. So therefore, the hardware component cost and also the power budget of your FPGA also has to be taken care properly. The next one is the short design time. So since in the nowadays in the market at a in a very short span of time, a different technology evolution will take place and different solutions for the same problem we will be getting. So the design time has to be as minimum as possible. So if your design time is as minimum as possible means, then whatever the solution we have come up with the market or we are going to come up with the market, so it will be persist for the longer duration. So if you are taking for the manufacturing itself for the longer time means, then the meantime some other vendors or some other architecture or because of the evolution in the technologies, so we can come up with another solutions by using a non-FPGA based components. Okay, so therefore the design time what we are going to do in order to do the implementation of FPGA based subsystem, it has to be minimum. Okay, so this is the abstraction of the FPGA design flow what we are going to do it. So at the first level we call it as abstraction. So in the abstraction what we are going to do is we are going to take the specifications from the requirements. So what exactly the problem? So what is the solution we are going to expect it? What are the constraints we need to do it? So all those specifications we are going to see at the initial stage. The next one we call it as a behavioral. So how that complex program we are going to divide it into subsystem and how the behavior of each subsystem has to be implemented. That is nothing but what is the input for the first subsystem, what is the output of the subsystem, and what is the relationship between the input system to the output subsystem. That we call it as a behavior modeling we are going to call it as. So means what, we are going to implement a program and those programs we are going to create it. So if you are getting the desired results means, then we go for the next step that we call it as a register transfer logic. So in the register transfer logic what we are going to do is, so whatever the program we have created in the previous step, so that we are going to implement through the use of RTL schematic. So if the RTL schematic we are going to get a desired results means, then we are going to represent in terms of logic gates. So once we come up with the logic gates means, then it is necessary for us to create the circuits based upon the functionalities what we are going to implement. Okay, so that we are going to do it through the use of a transistors. So the logical level implementation will be converted into circuit level implementation, and finally the circuit level implementation will be gone into layout. That is nothing but a mask layout we are going to do it. So when you do that, when we are going to use the stick diagram implementation, that is a layering architectures, we are going to use it, and after layering architecture we go for the mask layout. So once the mask layout is ready, then we go for the fabrication of this mask layout. So in the fabrication of the mask layout, so which type of mask fabrication you are going to take it, that depends upon the what is the applications you are going to do it, and what is the design methodology you have taken for the implementation. So based upon that, your layout representation will be taken place. So it may be CMOS fabrication process, or it may be NMOS fabrication process, or it may be by CMOS fabrication process we can able to implement. So this is the general architecture of your FPGA based design flow. Okay, so in terms of functionalities we have represented the left side, and in terms of cost wise we are going to represent at the right side. You can see here in the layout we will be having in terms of microns, and whereas in the case of circuits we will be having in the case of nanoseconds delay functions, and in the case of logics, so we need to go for the power optimization, the gate depth, and the literal constants what we are going to use for the logic implementation, that we are going to see it. And in the case of resistor transfer logic, so what is the functional unit of each subsystem we are going to see, and how many number of clock cycles we are going to use for the implementation of each subsystem we are going to look at. And the next one is in the behavioral, we need to measure the throughput and the design time. So if your throughput and design time you have properly defined and clearly come up with a proper abstract level solutions, means then the cost of implementation will also can be minimized properly. Okay, so this is, we call it as an abstraction of FPGA design. So we discussed already this FPGA architecture. So this FPGA architecture is mainly consisting of a combination of logic, interconnects, and the IO pin. So how the structure of this FPGA fabric will look like, will be represented in this diagram. So each logic element, it has been connected to the input output blocks, and the logic element to the IO block we are going to do the interfacing through the use of programmable logic elements. So you can see here we have a row of logic elements, and each logic element, it has been connected to the IO block. So the input will be fed from the IO block, and the logical operations will be done, and the output of these logical elements will be fed back to the IO block. In order to have a communication from one logical entity into another logical entity, we are going to use a programmable interconnects. So through the use of programmable interconnects, so the logical elements have a communication from one entity into another entities. We call it as a interconnectivity with a complex path. So if the implementation of your logical operations or the application, if it is more, means then one logical element has to be connected with another logical element, and if they are very far apart, means then the routing how we are going to establish between one logical entity into another logical entity, so that plays a very important role. So here you can see here the interconnectivity, it has been very complex path. So from logic element, it has to vertical channel we need to create. From the vertical channel, it has been gone into horizontal channel, and from again vertical channel into horizontal channel, and again it has been connected to the logical elements. So the placement and routing of your FPGA components plays also very important role in the design aspects. So the routing what we have used, so what we are going to do is the power, the data bus and address bus, we are going to use a minimum values for the interconnection of logical elements. So if we use a minimum interconnection elements, means then the power budget also we can be able to minimize. And if you do the floor planning of the placement of this logical element has to be properly, means then we can minimize the wiring which is necessary for us to do the logical elements. So since you can see here it is using 1, 2, 3 vertical channels it is using, and 3 horizontal channels we are using. But if you place these logical elements very close apart means then we can minimize this vertical channels or horizontal channels. So with the use of these minimizations we can improvise the power budget of an FPGA fabric implementation. Okay, so this is about your interconnectivity with the complex entities.